All right, so next up, continuing with the baseball theme, we have The Wrong Stuff by Liam Jennings and Belle Schmidt. This is the project in partner with the Pittsburgh Pirates. So Liam is a senior at Robert Morris University, majoring in statistics and data science with a minor in sports management, and is also pursuing a master's in data science. In addition to his coursework, he's the Sports Analytics Club co-founder and president, Analytics Club vice president, and also an honors first-year seminar program mentor and men's club volleyball captain. After graduation, he is excited to start a career in data science with aspirations to be in the sports industry. Belle is a junior at St. Olaf College, majoring in math, concentrations in stats and data science, and management. At St. Olaf, she's heavily involved with the athletic community, is a member of varsity softball, does data analytics for the football team, is the president of the Sports Analytics Club. Outside of academics and athletics, she enjoys listening to music, Chinese restaurant, and traveling. After graduation, Belle hopes to work as a data analyst in the sports industry. So guys, take it away.
Awesome. Thank you. Thank you for everyone for coming here. Also, we'd like a big shout out to our project advisor, Sean Ahmed, and how much he's helped us with this project. I'd also like to thank Dr. Yurko and Kwong for a fantastic summer and everything that you guys taught us. And I know we're going to use it well. So thank you. We'll start with, this is our project, The Wrong Stuff. I'm Liam Jennings.
And I'm Belle Schmidt. So I know the last group already touched on it, but Stuff Plus is a pitching metric that evaluates a pitch based on physical characteristics, or so we thought. Recently, there was more information published that it also includes other metrics, but velocity, vertical and horizontal movement, extension, spin rate, spin axis, release point, and velocity and movement differences from the primary pitch. When we talk about the nastiness of a pitch, it's kind of like getting a chair pulled out from underneath you, where you think it's right there, and then last minute, it's just not. The main questions we wanted to answer with our research this summer was, what variables are most important for an effective pitch? We wanted to know how well the Stuff Plus model is evaluating the effectiveness of a pitch, and how has Stuff Plus and the effectiveness of pitches changed over time. We used two main data sources. We used Fangraphs, which provided us with the average Stuff Plus in a given season for each pitcher's pitch types. And then we also used Baseball Savant, which provided us StatCast pitch-by-pitch data, which then we calculated the aggregated physical characteristics of a pitch, release point, expected weighted on base average, and whiff percentage for each pitcher's pitch types in each season. We initially looked at the four-seam fastball. The purpose of the four-seam fastball is that it's a high pitch with a high velocity. It's the most commonly used pitch in the MLB currently and has become increasingly popular over the past couple of years. But intuitively, it would make sense that because it's become more popular, maybe it's becoming less effective. And so two players where we saw this was the case, Andrew Heaney, he had above average velocity extension below average, velocity extension and induced vertical break with above average horizontal break and spin. Stuff Plus valued him at average, yet he was performing above average for whiff percentage and expected weighted on base average. Julian Merriweather, on the other hand, had above average velocity extension and induced vertical break and below average horizontal break and spin rate. And Stuff Plus valued him above average, yet he was performing below average.
And we really use some real household names. So before I talk about this plot, I'm just going to explain it a little bit. So the x-axis is horizontal movement, and that's just how much a pitch obviously moves horizontally. The vertical movement axis is induced vertical break, and what that is how much it would rise based on spin rate if gravity were not impacting it, because obviously a pitch cannot increase 20 inches as it gets towards the plate. That is physically impossible, unless you're Paul Skeens. And so the black lines in the plot, those represent 0 inches of horizontal and vertical movement. So that would just be a pitch thrown straight forward based on what it's classified as. The red lines, so the vertical red line is the average horizontal movement of a four-seam fastball. And the red horizontal line is the average movement or the average vertical movement of a four-seam fastball. So you guys are going to see a couple of these plots. So sorry, it'll take a little bit to get used to. But the first things we looked at were the outcome variables, which are whiff rate and expected WOBA. So for whiff rate, the common theme or the common theory in baseball is that these high induced or like the high vertical movement fastballs are going to generate a lot of whiffs because they have a lot of velocity and they're coming at you and they appear to rise right in front of you. Which you can see the majority of that is the top half of the plot. And you can see throughout the years that maybe this isn't the case, that maybe these pitches in the bottom right quadrant, which are above average horizontal movement pitches and actually below average vertical movement, seem to be generating more whiffs. So next thing we took a look at was expected WOBA. And so in this case, the lower your expected WOBA is, the better that is. And that's just supposed to show like how good an offensive player is, or I guess how good a pitcher is in this case. And once again, we saw the same similar trend of the bottom right quadrant has these above average expected WOBA values, which started to make us consider, like, is this general theory, is this really proven as effective as it used to be when it first came out in the pitch tracking StatCast era? So we decided to look at Stuff Plus on the same plot. And as you can see here in this bottom right quadrant, all these pitches that are generating high whiffs and low expected WOBAs seem to have below average or about average Stuff Plus. And meanwhile, the high vertical moving pitches seem to have the highest Stuff Plus, and they're the only fastballs that are really above average. So we thought that was really strange. And before we go into the modeling, I also want to talk about sliders. And as Danny had talked about earlier, he was talking about the classification type between Fangraphs and Stuff Plus, or sorry, Fangraphs and StatCast. And Fangraphs does not have sweeper as a pitch type, and they do have sliders. So all sweepers are just considered sliders, despite StatCast using their pitch-by-pitch data where they have sweepers and sliders. So the initial thing is when we looked at this is if you take a look at the red vertical line, to the left of that, all those pitches generally have below average velocity, and it just seems to be a direct split in the middle. And you might think, oh, that's kind of a weird trend. You take a look at spin rate, obviously spin rate and velocity are correlated, and you notice the exact same thing of these pitches that have above average horizontal movement for sliders have low velocity and high spin rate, and all the pitches with a below average horizontal movement have above average velocity and below average spin rate. So we decided to use the StatCast data to take a look at the average physical characteristics for sweepers and sliders. And the one that sticks out the most is the difference in average horizontal break for sliders and sweepers, where it's almost a 9-inch difference. So we decided to plot that on here. So just for example, so the purple line, the thick dashed purple line represents the average horizontal movement of sweepers, and the dotted lines represent the standard error of that. And then the thick gold line represents the average horizontal movement for sliders, and the dotted lines once again represent the standard error there. So you can see that these confidence intervals do not overlap with each other, and that these should be two separate pitch types because they're nowhere near similar despite Fangraphs ranking it that way.
So the first question we wanted to answer was the Stuff Plus model changing year by year? And so we did this by putting a single physical characteristic of a pitch on our x-axis and then Stuff Plus on our y-axis, and we did that for year by year. In the graph, you guys can see we have induced vertical break on our x-axis. And looking from this graph at the slope specifically, we can see that it's not really valuing additional induced vertical break differently each of the years. Now, from there, we want to know if the physical characteristics are impacting outcomes differently year by year. Again, we followed the same methods for the graph, but instead we have different outcome variables on our y-axis. So in the case here, we have whiff percentage. Again, looking at the slopes, we can see that vertical break is impacting whiff percentage very differently year to year. So from here, we wanted to answer the question of how well is Stuff Plus adjusting year to year. We did this by fitting linear models for different outcome variables. So we did Stuff Plus, expected weighted on base average, and whiff percentage. We did that based on a single physical characteristic and season, and then the interaction between those two variables. Then we put it in a graph, and here you can see that we have year on our x-axis and then change in stuff plus per inch of induced vertical break on our y-axis on the graph on the left. From this graph, you can take away that stuff plus is how it values induced vertical break or additional induced vertical break slightly year by year, but not too much, and that each year it's having additional induced vertical break as a positive thing. Then on the graph on the right, we have the change in whiff percentage per inch of induced vertical break. Here we can see that there was quite a significant change from 2021 to 2024. From 2021 to 2023, having additional induced vertical break is still a positive thing, although it's decreasing. And then in 2024, it's no longer really making much of an impact. And then again, now you can see change in expected weighted on base average per inch of induced vertical break. And in 2021, 2022, and 2024, we can see that having more induced vertical break was actually a bad thing. For those of you that don't know, expected weighted on base average, you're gonna wanna have as low as possible as a pitcher. So looking at these two plots, we can see that maybe Stuff Plus is not valuing vertical break well, and that maybe it shouldn't be valuing it as positively as it is.
So then we decided to simulate the actual Fangraphs Stuff Plus model, which we learned is trained on or using an XG boost model. However, we also considered random forest just to see if it would perform better. So using 5-fold cross validation, the XG boost model ended up being the best based on test MSEs. And so what we ended up doing was we decided to look at the variable importance for each model, at each XG boost model that we made. So there's a different model for each year. And looking at this plot, we can see there's going to be 5 data points for each year, despite there being 11 characteristics in the model. The reason for that is because I didn't want to put 11 lines on there because it would look ugly and it'd be hard to see. But also it's easier to see which are the most important variables. So you see, for example, for 2021, we have 5 data points, 2022, we have 5 data points, and so on. And what this says here is the most important variables for Stuff Plus are the variables that are in the model or in each model, which would be spin, velocity, extension, and horizontal release point, which kind of goes back to like Stuff Plus is very dependent on spin and velocity. And what we want to compare this to was using the same XG boost model for each year. We looked at expected WOBA and whiff rate. And as you can see that the variable importance plot is very different. The most important variable is velocity difference. And what the velocity difference is, that represents the difference in that, or the velocity of that pitch minus the velocity of the pitcher's fastball. So thinking of a pitcher, Dr. Irko, you said Paul Skeens? Yeah, Paul Skeens has an average four-seam fastball of 99 miles an hour, and his sweeper is about 85 miles an hour. So that's a 14-mile-an-hour difference, and that's huge. And the reason that velocity difference is so important is because hitters are able to calibrate their timing based off of their primary fastball's velocity. So that's why we believe that velocity difference is the most important for expected WOBA, and it's not really even close. And when you take a look at whiff rate, you realize the same results is that this velocity difference is generating very low expected WOBAs and very high whiff rates, or it's most important in predicting these two outcome variables. So in terms of our discussion, we've realized that there is some bias in the Fangraphs Stuff Plus model, which we talked about with pitch types and also maybe just the way that the model is trained, is that it's favoring certain variables that aren't reflected in outcome variables. So maybe Stuff Plus is not the best predictor of how a pitcher is actually performing. A pitch may be filthy, but it's not going to lead to maybe good results on the field. Obviously, there are some limitations to our work. We used aggregated data because there's not pitch-by-pitch Stuff Plus data. So we had to aggregate our StatCast pitch-by-pitch data and combine it with the annual or the yearly Stuff Plus for each pitch type. And as I already mentioned, we had limited pitch types, and also the temporal scope wasn't the best. Stuff Plus was created in 2020, so it was trained on 2019, which we know as the juice ball. And obviously that's not the best way to have this. And obviously now that it's been built over time, but still we only had data from 2021 to 2024 because we didn't want to use the COVID season since it's not a full season and it's not the best way to represent our data. Possible future work is we want to look into other pitch types to see if there's any biases in Stuff Plus there. And also maybe possibly create an open source Stuff Plus model. I think that'd be something to look into, especially since with the public data that we have. So yeah, thank you. What questions do you guys have?
Thank you. All right. We'll pause on the questions for the students. We'll take that to the break. So make sure during break times up ahead, you find these students, you talk to them, you give them job offers, etc. All right, let's give a big round of applause for the students and also Kwong. All right, so we're going to do one more talk before break.